Hello guys, so welcome back to our lecture. So in this lecture, we're gonna, build a more complex comparator, binary comparator. So in our last video, we built the one-bit comparator, which is basically a simple circuit that compares only two bits together. I mean, you have two inputs, each input is one bit, only one bit, okay? And this, we see that this circuit has three outputs, okay, which represent the three cases, A greater than B, A less than B, A equal to B. Okay. Now, if you have, a more complex or more bits in your inputs, A and B. So, for example, if A is more than one bit, 4 bits, for example, and B again is 4 bits, how are you gonna compare them? Okay. So we need to build, another circuit basically. But then, if we think in the same way that we think about the 2-bit comparator, it will be cumbersome. Let's see how. So we build the 2-bit comparator using the truth table. So we build the truth table for the design. We express the output in each case of each combination, basically, of the inputs. Okay, and build, Karnaugh map. It was really easy. So let's do the same here. Let's check. So you have two inputs, but each input is 4 bits. It's like if you have four inputs for each one. So totally you will have 8 inputs. So look, for A, you will have A3, A2, A1 is 0. Then for B, you will have B3, B2, B1, B0. Then you will have 3 outputs. Let's call them A equal to B, E capital. A less than B is L capital. A greater than B is G capital. So E, L, and G. But then you will have here 8 inputs. That means you will have, 256 combinations, which is basically cumbersome. You cannot do that, and you will have errors, many errors basically. Okay. So it's hard to design, hard to trace, hard to debug. Everything is bad here. Okay. So is there another way to do that? Yes. And again, the answer, like all our previous designs, we think in a hierarchical way, or a modular way, or structural way. Okay. So we have already a module called 1-bit comparator. Okay. Can we use it? And the answer is yes. So let's see how. Okay. Let's check, some cases for A and B and see or guess how would be the output E or L or G. Okay, let's see, for example, A is equal to 1100, which is basically 12, 8 plus 4, and B is equal to 0111, which is basically 7. Okay, of course, 12 is greater than 7. So in that case, we expect that we have 0 at E, 0 at L, because A is not less than B or equal to B. It's basically greater than B. So G will be 1 in that case, and the other outputs will be 0. Okay. So look at these two numbers. You will find very interesting thing here that, look, A3 is greater than B3, and that's enough. That's enough, basically. Whenever you see A3, I mean the most significant bit of A, greater than B3, that means that E will be 0, L will be 0, and G will be 1. Okay, good. How about another example? Let's take, for example, A equal to 0, 1, 0, 0, and B is equal to 0, 0, 1, 1. Okay, here we have another interesting, example. So this is basically 8, this is basically 3, and of course 8 is greater than 3. Let's check. Look, A3 and B3 are equal. So here A3 equal to B3, but A2 is greater than B2, and you don't need basically to check the other bits. I mean A1 and B1 and A0, B0. Also, if you check, A1 is less than B1 and A0 is less than B0, but since A2, is greater than B2, then for sure, A is greater than B, and in that case, G will be 1 again, and L will be 0, and D will be 0. Okay, so we can deduce the following, that G is equal to the following, or will be 1 in the following cases: First, the first case is if A3 is greater than B3. This is the first case in which G will be 1. Another case is A3, A3 is equal to B3, but at the same time A2 is greater than B2. Another case, A3 equal to B3 and A2 equal to B2, but this time A1 is greater than B1. And the last case is all of them are equal. I mean A3 equal to B3 and A2 equal to B2 and A1 equal to B1, but at that time A0 is greater than B0. That's basically G. So you have 4 cases. So it will be 1 in any of these 4 cases. So basically you can connect between them using or here, then another or here, then another or. Okay, it's like 3 terms. Okay, so good. Can we deduce another one for example E? Yes, we can do that. Let's try another color. So basically, let's check another example in which A is equal to B. Like for example, A is 1101 and B is 1101. Yeah, they are equal to each other. But look, A3 is equal to B3. And A2 is equal to B2. A1 is equal to B1. A0 is equal to A0. So E, the first output here, will be 1 only if all the bits or all the corresponding bits are equal. I mean A3 equal to B3 and A2 equal to B2 and A1 equal to B1 and A0 equal to B0. How about L? You can make L something very similar to G here. Very similar. Okay, so for L, it will be, let's do that with so L will be 1 if first A3 is less than B3. Okay, so for example, A is equal to, for example, 1 or 0, 1, 1, 1, and B is 1, 0, 0, 0. This is basically 7, and this is basically 8. And of course, 8 is greater than 7. But look, here, so basically here, A is less than B. Okay, why? Because A3 is less than B3. So you can build something very similar to this, but you will just, convert this greater than sign into less than sign. So for example, L will be equal to A3 less than B3, or A3 equal to B3 at the same time, and A2 is less than B2, or A3 equal to B3 and A2 equal to B2 and A1 now less than B1, or finally all of them are equal except the last case A0 B0. So here is A2 equal to B2 and A1 equal to B1, and finally A0 now is less than B0. Like for example, this case here, A is 0, 1, 1, 1, 0, and B is 1, 1, 1, 1. Of course, this is 14 and this is 15. So, and of course, A is less than B, or 14 is less than 15. Okay, guys, that's basically, G, L, and E. Now, how we design that? Okay, so basically we're gonna compare each corresponding bit together. So basically we need 4 1-bit comparators. This is number 1 or let's call it number 0 because it's comparing A0 and B0. This is number 1, this is number 2, this is number 3. But they are 4, okay, from 0 to 3. So one binary binary comparator is comparing A0 B0. The second one comparing A1 B1. Third one A2 B2. Fourth one comparing A3 B3. Okay. Now here is the outputs. Here is basically the outputs. Okay. You have 3 outputs of the first one, another 3 outputs for the second one, another 3 outputs for the third one, another 3 outputs from the fourth one. So what we really need is something saying A is less than B or A is greater than B, right? And that's basically what we have. So A0 means that A0 equal to B0. L0 means that A0 is less than B0, which is, for example, that condition here. And the G0 means that A0 is greater than B0, which is basically that condition here. Okay, so these are the conditions. Okay, so if we want to represent G or L in terms of E0, L0, G0, or E1, L1, G1, and so on, it will be something like this. So for example, let's do the L. For example, L equal to, in terms of these outputs here, these internal signals, okay? L will be 1 if A3 is less than B3, which is basically L3, this one. Or A3 equal to B3, which is basically E3. And A2 less than B2, L2. Or A3 is equal to B3, so this is E3 again, and A2 equal to B2, this is now E2, and A1 is less than B1, which is L1. So, and finally, this last case here, A3 is equal to B3, which is basically E3, and A2 B2, which is E2, and A1 B1, which is basically E1, and finally A0 is less than B0, this is L0. Okay, this is basically L. We can write it concisely again like this: A is equal to L3, or, which is plus sign, okay, E3 and L2, or E3 E2 L1, or E3 E2 E1 L0. Okay, so basically you will have 3 equations like this in your VHDL code, for example. Okay, and that's basically would be the final design. So this is a circuit. This second stage here is basically a circuit, you know, a digital circuit, of course, that will produce this final outputs for you, like L and G and E and E, based on these internal signals. So, for example, this will be as a design in our code will be 3 lines. One line is this, the other line is for G, and the third line basically is for E. Okay, that would be basically our design. Okay, guys, so this is basically how to think about it and how to design it. In the book, you will find this circuit that exactly do what we need. Okay, and look, this is basically the first 1-bit comparator. This is basically, this one here is basically number 0. And this one, oh, I'm sorry, so because it, yeah, so it started from 0 in the bottom and then go to, so this is basically the 4th comparator, which is basically that one. Okay, and then this is the, you know, the 3rd one. If we go up a little bit, this one here is basically that one. Okay, then this is the 2nd one, and this is, you know, the 1st one here. Okay, now where is E0, for example, L0, G0? So let's check them out. Of course, L0, A0, E0 should come out from your this one here, which compares E0 and B0. So let's do that. Let's find out. We know that L0 means A is less than B, which is A0 and B1. So this will be A0 bar B1, because B0. Because B0 should be 1 at that case, and L and A0 should be 0. Okay? So look here where we can find that. So this AND gate compares A bar or A prime and B0, E0 and B0. Okay, so the output, this output here is basically L0, which is A bar B0 or A0 bar B0. Okay, this second AND gate has 2 inputs, A0, this is A0 basically, and this is B0 complement. So the output here, this output is E0, B0 complement. This is basically G0. Okay. And where is the equality? This is the equality, X naught here. So basically X0 in this design is basically E0, but you know the book called it X. I prefer E. Okay. So you will find, so we know that E0 should be A0, B0 plus A1, B1, A1 bar, I'm sorry, A0 bar, B0 bar. Okay, this is what we get from our last design, right? From our last recording. Although it's different in here. So it's written basically as A0, B0 bar plus A0 bar, B0 complement. Remember, guys, this is basically XOR. And we know that XOR complement is just X NOR. So what's between the parentheses here is XOR. Then you take the complement, so XOR complement is basically X NOR. So it's the same. It's not different. Okay? So we can say this is equivalent to what we have done. It's not exactly the same, but the same function. But a small tweak, you know, to how to represent or how to implement the X NOR. Okay, so it's not a big difference. So basically, it's a small tweak how to implement the X NOR. So he implements X NOR as XOR complement. Okay, guys, that's basically, you know, the design and how we think about it and how we deduce it. Okay, it's really simple. Okay, so it's time now to explore the, you know, how we gonna code this in VHDL, either the simplest one bit comparator or this more complicated one, which is compares 4 bits together. Thank you very much for watching this video, and see you in the next video. Bye bye.